Okay, so I'm just going to start by thinking, I'm going to actually start with a roadmap. Just to give you a sense of what we'll talk about today. This is going to be a really high level, kind of 10,000 feet summary today to try to get folks who have maybe not had much exposure to causal inference to maybe get excited about it and want to do more work in the area. I think it's a super important part of statistics and data science. So maybe by the end of my talk, you'll agree. So first, I want to try to give some motivating examples for why causal inference is important. Tamped down by the realization that causal inference is also really hard. And then I'll talk a little about the role of machine learning, both in terms of how it could be great for causal inference and what might be problematic. We'll talk about the role of humans in this whole process because we influence it as well. And then I'll do a shameless promotion of some software I'm developing. Okay, so I couldn't do anything I do without lots of collaborators, lots of brilliant minds who have been fantastic in helping to push me and to co-develop lots of different things over the years, and also generous funding from the Institute of Education Sciences and the Office of Naval Research. Okay, so we'll start by talking about why causal inference is important. So I would argue that almost every important research question we want to answer is causal. So if you just grab some headlines, these are headlines from national paper. Does abstinence-only education work? Can gay marriage solve our adoption problem? Does exposing preschoolers to music make them smarter? Did the introduction of City Bike make New Yorkers healthier? Does the death penalty reduce crime? Would a Medicare for All plan help you save money on your family's healthcare costs? What happens when the poor receive a stipend? If you start noticing headlines in newspapers, you will notice that lots of them are causal. If you start thinking about the questions you'd like to answer to solve the world's most pressing problems, they're probably causal questions. That means if you want to get good answers or estimates of those answers, you're going to have to think causally. Luckily in Montreal, you've got lots of fantastic causal researchers. It's not true of all places in the world. So you've got lots of resources where you're at. All right, so these are all causal questions. And the question is, what's the cost if we're wrong? Maybe we don't get it right. How bad could it really be? So I'll give just two motivating examples. One is the Salk vaccine, which I almost stopped using in lectures when COVID started, but I actually think it's more important than ever to think about these issues, and particularly in contexts where we need vaccines. And then the second is feels a little less close to the heart, but internet ads. Okay, so let's talk about polio. For those of you who are younger, this may seem like just the name on a vaccine you got when you were a kid, right? You probably didn't live through the era of iron lungs and paralysis and, games getting canceled for a different public health crisis than the one we're currently living through. But polio is a really devastating disease characterized by progressive muscle and joint weakness and pain, sometimes leading to paralysis. Well, I'm not quite old enough to have lived through it. I certainly have relatives. I had a grandfather who one whole side of his face was paralyzed because of polio that he had as a child. And but most of those generations aren't around anymore to tell us their stories. The first major polio epidemic in the United States was in 1916, where 27,000 people suffered paralysis and 6,000 died. By the 1950s, polio was responsible for 6% of all deaths among 5 to 9-year-olds in the US. And while the disease was fairly rare, the virus was fairly common. If you're wondering how this all played out in Canada, was Canada spared? Well, an estimated 11,000 people in Canada were left paralyzed by polio between 1949 and 1954. disease peaked in 1953 with nearly 9,000 cases and 500 deaths. It was the most serious national epidemic since the 1918 influenza pandemic. So what were we to do? This was a period of time when the idea of vaccines existed, and indeed some vaccines had been created over the years. It wasn't an entirely brand new concept, but it certainly didn't have the acceptance that it currently does. So when someone named Salk tried to get people to accept the idea of a vaccine, it was not readily accepted. And in fact, in the beginning, all we had was observational evidence. So in 1954, the US Public Health Service investigated the effectiveness of this vaccine. But the observational evidence, so here they're comparing people who got the vaccine with people who did not, it didn't look so great for the vaccine. It wasn't looking super successful. However, a randomized experiment was then conducted that demonstrated the vaccine was indeed effective. So how did that happen? Well, it turns out that the people who got the vaccine were quite different than those who didn't. They were far more resourced. There's lots of different stories and conspiracy theories. You can go down that rabbit hole on the internet, but one of the more commonly accepted ideas was that actually those who received the vaccine were from wealthier backgrounds. And this was not an era where parents were taught that, let your children eat dirt, it'll expand their microbiome. So actually, the wealthier kids didn't have the immune systems to fight off the disease, so they were at a disadvantage from the get-go. So that was an interesting example, also because the bias went in a direction that was different than what had been anticipated. Okay, so then we have this big success. We have headlines like this. There were parades for Salk. There was a great article actually in the Post the other day about the difference between how the US at least reacted to the Salk vaccine versus the COVID vaccines of late. Anyway, quite a different reaction. Salk vaccine saved lives because of evidence from a randomized experiment. This is really, really compelling evidence. Okay, and this in part, along with lots of other things that were happening at the time, led to the development of FDA standards for drug approval that required clinical trials. It led to organizations being built like the What Works Clearinghouse in the education world and the Cochrane Collaborative that accumulate evidence about various kinds of interventions or drugs that are based on randomized or either randomized experiments or very rigorous quasi experiments, right? And they really set up a standard for what it means to estimate something causal. So this all seems like a move in the right direction. And you'd think that after that, we have learned our lesson about the importance of thinking carefully about causality. But then flash forward about 60 years, and we have big data, and we have fancy machine learning methods to analyze it. So you'd think this would make things easier, and yet we started to see headlines like that. And articles that said things like, this is a quote from this article, "There's now a better way. Petabytes allow us to say correlation is enough." And there were arguments being made that if you have enough data, it doesn't matter if you use the right design, right, or the right analyses, correlation should be enough. Like as if the problem before had just been about like inadequate sample sizes, right? Whereas that's not actually the problem. So big data in that case led to big hubris. So let's look at another example that's from the much more recent past. Do click-throughs on ads on the internet lead to more money? So there is this prevailing belief that if you advertise on the internet and people click on the ad, that must mean the ad is working, right? To induce people to buy your product. So the common wisdom is internet advertising is highly effective. And in fact, in 2011 in the US, $31.7 billion were spent on internet advertising. That's a whole lot of money. So from that perspective alone, you'd think we really wouldn't want to spend all that much money, or that firms wouldn't want to spend that money if it wasn't actually making a difference. What are the data being used to analyze whether or not internet advertising was effective? Well, basically, did you click on the ad? Did you buy the product? Maybe a little more than that, but mostly it was that combined with fancy machine learning algorithms, which if you don't have that many variables, maybe was a logistic regression at that point. Okay, so the causal question here is, what if shoppers would have bought the product anyway, right? So there's this cartoon that shows the man seeing this shoe, an ad for a shoe on television, ad for a shoe on his computer, ad in his car in the jingle, and then sees something on his phone and buys it on his phone, and the advertisers think, oh, it must be the phone ad that did it, right? And this is basically the same idea. More generally, marketers want you to believe that if people see the ad, they will buy the product, or there's a much higher probability that they will buy the product. If they don't see the ad, there's a much lower probability. But what if the truth is that someone just wants to buy that product? They may see the ad, they may not see the ad, but they pretty much were going to buy it anyway. And for some range of products, that's going to be closer to the truth. So how can we tell? Maybe we could do an experiment, or in fact, eBay did a quasi experiment where they alternated weeks of advertising and showed that for a particular set of products, 99.5% of purchases happened without the benefit of an ad, meaning the ads weren't really making a difference. And yet in 2020, 152 billion spent on internet advertising, 378, oh, sorry, I'm jumping up, 378 in 2020. So it's not clear that the lesson was really learned. So we ignore causal inference at our peril. Okay, let's talk about why isn't everyone doing the right thing to estimate things causally, right? If this is so important, why don't we all always use the right method or the right design? And the problem is that it's hard, right? So to understand why it's hard, let's look, we'll review some building blocks of causal inference. So first we'll talk about counterfactuals. Joe on a Saturday sees an ad for an iPhone, or in an alternate universe, Joe, same universe, Joe the next Wednesday buys that iPhone. So we've got a treatment realization, Joe seeing an ad, and we've got an outcome, Joe buying the iPhone. Did the ad cause Joe to buy that iPhone? Well, we don't know the answer to that without knowing what Joe would have done if Joe had not seen an ad, right? We need the counterfactual. So what we really need is to be able to bounce between two alternate universes, one where Joe saw the ad over here, one where Joe did not see the ad, and then look in each case whether Joe bought the iPhone, right? We don't know how to even define a causal effect without looking at that comparison. The problem is that we only get to observe one of those. We don't get to bounce back and forth between alternate universes. We don't have a time machine to go back in time and prevent Joe from seeing the ad, or give the ad to Joe if they had not seen it to begin with, right? So we don't get all the data we need. We have a missing data problem that's very difficult to resolve. And yet we want to answer things like, optimally, we'd like to know the causal effect for Joe, right? If you're thinking about the effect of a drug or a medical treatment, you don't actually care what happens on average. You want to know for you. But that's the hardest of all of the causal quantities. So usually we back up to some kind of average treatment effect. So the average treatment effect for everyone we have data on, or the average treatment effect for everyone who saw the ad, those who were treated. Okay, so what would our assumptions be if we want to estimate things like that? So I'm going to break this into two categories, structural and parametric, and I'm going to hand wave a lot and leave a few things out in service of getting done on time. Okay, but any course on causal inference will teach you these things. So the basic idea that's reflected in the assumptions is that causal inference is about making fair comparisons. If you're comparing two groups of people and one group got a treatment and one group didn't, you want to be able to rule out all the other possibilities for why one group looks different from the other at the end of the day. So you want a level playing field. Technically, what we want are balanced distributions of our potential outcomes, those outcomes we just talked about across the two groups. And that might be unconditional balance. Like, so if we have a randomized experiment, those should be unconditionally balanced. They might be conditionally balanced in other kinds of designs. So we call that assumption, that fair playing field assumption, ignorability, where X here again measures pre-treatment covariates, and Z is just a binary treatment assignment. Ignorability is also called different things in different disciplines. So some other names that it goes by, no hidden bias, selection on observables, all confounders measured, exchangeability, exogeneity. There's a bunch of different, I'm sure there's several others. Okay, so again, randomized experiments balance those distributions of potential outcomes across the two treatment groups unconditionally, if it's a completely randomized experiment. Randomized block experiments do the same thing within blocks. So conditional on block, I'm getting that fairness property, okay? Now, often we are not in a position where we are able to create a randomized experiment or a randomized block experiment. We're not able to randomize at all. That could be for logistical reasons, financial reasons, ethical reasons, and some treatments just aren't manipulable, in which case actually you probably shouldn't be doing causal inference on it anyway, but that's a whole nother lecture. Okay, so observational studies look a lot like, the assumptions for them look a lot like the randomized block experiment, right? The key difference is that in a randomized block experiment, we know what the blocks are, we know how things were, and then we know that things were randomized. That actually happened, right? So this is less of an assumption and more a, can everyone see the message that just popped on my screen from my daughter? No. Good, I'm happy to hear that. All right, good. In this case, X is not known. We don't know what X are needed to satisfy this independence assumption. So we're guessing at what the confounders are. Okay, so we want to say that if we measure enough things and condition on them, then within groups of people who are similar on all their covariates, because X could be a 200-dimensional thing, then we've got independence between potential outcomes and the treatment assignment. In other words, it's like we have a coin flip at that point about whether or not you got the treatment. Okay, so in observational studies, this typically requires measuring and appropriately conditioning on lots of pretreatment variables, right? Those pretreatment variables or confounders are things that predict both treatment assignment and the outcome. And there could be lots of them. And you may not be able to measure all of them, right? Some things are very difficult to measure. But often what people do is just throw in as much as they can to try to defend against, you know, the referee down the line who says, oh, but you didn't measure motivation. That could really be the thing that's driving both why the person got the treatment and their outcomes down the line, right? So you're guarding against that, but in doing so, you're going to make your life harder in other ways, as we're about to expand upon. Okay, this is one of my favorite cartoons. I'm going to take a sip of water while you drink it in. Okay. So yeah, I know it's sad. Poor little guy gets a nice idea about something that might exist in the world, and the data lot comes along and says no. So what are parametric assumptions? So say we had a completely unrealistic situation where we have some treatment observations, they're in red, some control observations, and we know for sure that we have one confounder and it's pretest. Okay, it could happen. We don't know. Not likely, but it could. So say that was the case. Then, and say that the true relationship between each of the potential outcomes of the pretest is displayed by these curves. Okay. So the true treatment effect, for instance, for someone with a pretest of 40, that means is just the vertical distance between these two lines. The true effect of the treatment on controls would look at, for each point here, what the true distance is between these lines and then average them up. I've only put 4 in. Same thing for the treated. And the true sample average treatment effect would look at the difference between those two lines for everyone in your sample. Okay. The problem is when we try to estimate those things by, say, fitting a regression, we run into problems really quickly. So one big problem is that this linear model, so I overlaid a linear regression here with the dashed lines. The linear model doesn't fit the truth well, right? And as a researcher, we don't know the truth. So we're just guessing based on the data. We fit a linear model and we don't know that it's wildly off base here and it's wildly off base here, right? It's almost less problematic that it's off the course a little bit here. So this is a combination of things. It's A, that we're fitting the wrong model, and B, that we're extrapolating over portions of the covariate space where we have no business being. We don't have any data for treated observations here. So why should we be expanding our line over here? Well, implicitly, that's what we're doing. I mean, this is a simple case of a regression with one indicator variable and one continuous covariate, and it's extrapolating all over the place, right? So often in intro stat courses, we teach students don't make predictions for values out of sample, but that's what happens in a lot of regressions, but it's just hidden because people aren't making these plots. People aren't thinking about overlap, right? So you're fitting the wrong model and there's no red flag, Stata or R or Python, whatever you use, nothing's giving you a red flag saying this is a really inappropriate model, okay? So there are some problems here. So satisfying ignorability isn't enough. We also need to get the right model, right? And linear models are not always the right model. So we need something that's more flexible, okay? Now, for the past, 30 years plus, almost 40 years now, people have been using propensity score methods, propensity score type methods, matching methods, weighting methods. A big part of causal inference and statistics has been focused on these types of models, which basically aim to do exactly the right thing in terms of making fair comparisons, right? Let's focus on the observations where we do have overlap. And maybe let's reweight them or do some matching so that they're more balanced, that the distributions look more similar in terms of the observed covariates, because maybe the distributions then will be more similar in terms of the potential outcomes. All great ideas. And the whole propensity score revolution, really, one of the wonderful side benefits of it is people started looking at their data more and seeing when they didn't have balance and seeing when they didn't have overlap and when they shouldn't be making inferences. The problem is that propensity score methods are an art form, you know. No one knows what good enough balance is. They're incredibly time intensive if you really want to do a good job. They're not great for individual level estimates because that, you know, those algorithms are not set up to create good pairwise matches. And so not great for heterogeneous treatment effect inference in general. And they could lead to all kinds of problems with p-hacking, garden of forking paths, lack of reproducibility, et cetera. Because there was a lot of just, oh, I'll try this now, I'll try that now, right? So enter machine learning to maybe save the day. So we had a negative machine learning example before, but maybe there's a positive role. And again, I'm cherry picking some examples. I'm by no means giving you the full breadth of ways in which machine learning is interacting with causal inference, either positive or negative. Just basically giving you kind of one example on each side. So how can machine learning help here? It can provide an easy and honest approach to adjust for covariates. That's all. It's nothing magic. But in terms of that, how do we solve the parametric assumptions problem? It works pretty well for that piece of it. So I will give you examples using one particular algorithm called Bayesian additive regression trees. It's developed by Chipman, George, and McCullough. I think it's great, but there are lots of other options, which I'll give you a list of them at the end. So what's the basic idea? The basic idea is to fit your response surface using a bunch of little subgroups. So I don't have any sense of what everyone's exposure is to machine learning. So I'm both going to do too little and maybe too much for those who already know it. But if you look back at something that looks like our original example, and for now, just concentrate on the blue line. The blue line is a simple tree fit to the data, which creates subgroups based on X. And then the fit of the data is just the mean of the outcome in those subgroups. So those subgroups are formed. The first subgroup is formed by looking at all possible subgroups based on partitioning the data using X and seeing which ones create the greatest, it's kind of a least squares kind of criteria flipped on its head. So you want groups where you're getting the most variance explained, okay? So the first split is on the two groups. That makes a lot of sense. So I've got a lot of the Y's up here, and then of the Y values down here, those two groups. And then within the controls, for instance, it splits just once, right? So I'm creating these two subgroups. And then it splits 4 times for that group. If you keep splitting and splitting and splitting, you'll eventually, well, actually, you'll eventually overfit your data is the problem. So regression trees alone aren't gonna be our answer because it's very hard to get a regression tree that doesn't overfit and that captures things like additive structures. So BART is actually a Bayesian version of boosted regression trees. The idea of boosted regression trees is instead of just using the fit from one tree, I'm going to use the sum of fits from a bunch of trees. So this is distinct from something like a random forest where you're doing a model averaging. This is the sum of trees. So you can think of that as, well, first let's fit just one small tree, where in this case, now I've expanded to more covariates. Perhaps first I split on treatment, and then on age within the controls and along pre-test based on the within the treated, right? And now I've got 4 subgroups. That's a very simple fit to my data, clearly would leave a lot of variance unexplained. Let's subtract out that fit from the outcome. And then to the residuals, fit another tree. Do the same thing again, get a fit, subtract it out. To those residuals, fit another tree. That's the basic idea. You might fit 200 trees. It's a pretty common number in boosted regression trees. Now, if you do that, you're probably also going to overfit, right? So how do we get around that? Well, it's basically you use a shrinkage strategy. You will multiply the fit from each tree by something small. And you're going to shrink all of those fits closer to 0. And that helps to avoid overfitting. How do you choose that small number? Usually cross-validation. So it's a really nice algorithm that does well for prediction. It just has a couple of things that statisticians don't love. It's got this arbitrary touting parameter that we have to either choose, and if we're choosing by cross-validation, we're not reflecting our uncertainty in that choice, so we don't love that. Also, it gives a great prediction, perhaps, but what is our uncertainty about that prediction? So what Chipman, George, and McCullough did, which was beautiful, and I encourage you to look at their papers, was to embed that in a likelihood framework. In fact, then they threw it into the Bayesian machinery. And so then basically the fit, this whole sum of trees ends up being a random variable. And the other random variable is just the residual error. The key to this is really, really clever priors that help to avoid overfitting. Again, I encourage you to look at their work. It's fabulous. And then it's fit using an MCMC algorithm. Okay, so then a simple BART fit to this is reflected in the red dashed lines. Okay, so how do we use this for causal inference? Well, more generally, we've got lots of covariates. We have one data set that we fit the algorithm to, and then we use that algorithm to make predictions. Oops. Here's a set of predictions for a data set that looks a lot like our original data set, but except for we've set everyone's treatment variable to 0. And here's a data set that's the counterfactual version of the same thing. All the covariates are the same. The only thing that's changed is that all of the treatments have been set to 1. So for each person, I can get a predicted Y0 and a predicted Y1. But the cool thing is that given that it's been embedded in this Bayesian likelihood framework, I can get more than that. I can actually get a whole distribution, a predictive distribution of the Y0s for each person and the Y1s. And then I can take the difference of those to get a distribution of the treatment effect for a given person. I can average them up to get average treatment effects for any subgroup that I'd like. So it's super flexible, which is really nice. So in our original example, for the treated group, I've plotted 95% uncertainty intervals for all the treated observations. And you can see that they're all the way along covering the true expectation of the Y1 for each of these observations. For the Y0s, it's a little tougher. So I've just done, again, 95% uncertainty intervals for the Y0s for each of the treated, right? So you can see once we get out here, the algorithm starts to get concerned because there aren't data to support what it's doing. So it reflects that uncertainty in the uncertainty, right? Which is fantastic, right? That gives us a real obvious sign that maybe this is an area that we don't want to be making inferences in. Okay. So here's just the requisite screenshot of articles. I'm sure there are more now that have been published about BART and causal inference, and some by me, some by others, some about competitions that BART has been in and done really well. And so that's great. It makes me happy. Some other bells and whistles, which I'm going to go through too fast for it even to be worthwhile for me to do this, but I just had to. Okay, so because of this property, actually I'm going to show it here instead. So here I've got the same example, but I removed that one point. I don't know if you remember, there was one point out there which was really anchoring things and making things easier. I've taken that away to make things harder. And you can see at some point you're drifting off, and if you try to make inferences for these treatment observations up here, you're not going to be doing a good job. So I wrote a paper in 2013 talking about how do you know how big do these need to get before you start to say, no, I shouldn't be making inferences there. Okay, it's a totally different approach to the common support problem than the propensity score approaches, which base everything on the propensity score, which can be problematic because the propensity score includes a bunch of covariates that may not be predictive of the outcome at all, in which case you don't need to be worried about lack of overlap in those. So sensitivity analysis. So also created a package called TreatSense that takes some existing sensitivity analyses and makes them more robust to parametric assumptions using BART. The basic idea here is to play the thought experiment of, well, what if there were one more covariate motivation that I forgot to include, or I couldn't measure, didn't measure? What if that were included? What would that variable have to look like? How strong would the relationship have to be between that variable and the treatment, between that variable and the response, before I started seeing treatment effects that were very different from the naive estimate I'm getting, assuming ignorability. This is a bad slide. This is just a list of papers that have been written about treatment effect, heterogeneity, and generalizability using BART. So again, as compared to a lot of the propensity score approaches, we think it ends up being a much stronger approach for these goals. And then finally, for treatment effect moderation, I'm just going to show you pictures. Basically, we've got a technique for treatment effect moderation that allows you to turn a plot like this, which is a plot we were presented with in a causal inference competition a couple of years ago. Two colleagues, Vin Story and Nicole Carnegie, and I were given data. We were asked to find moderators. We first made a bunch of low S plots looking at treatment effects that came out of BART versus two of the covariates we were asked to consider as potential moderators, and we didn't see, it was very difficult to interpret the results. And then I made these scatter plots of treatment effects at the school level versus the moderators and thought, well, that's weird. What is this group down here? This is not something you can get from a propensity score approach, right? Because you would never be able to pull off these school level effects. But when we threw those treatment effects into a classifier, into just a plain old regression tree, it popped out that what really was at play here was a variable reflecting how urban the school district was. Okay, so we were able to quickly identify a key moderator, something that none of the propensity score approaches that there were 13 different competitors or 11 or something. Anyway, none of the propensity score people found this moderation. Okay. So anyway, all of these things, all these bells and whistles are wrapped up in a package called BART-CAUS that sits on CRAN, except for when we're getting yelled at by the CRAN hierarchy and have to take it off and fix things and then put it back on. But I'm sure many of you have been through that drill, but usually it's there. And if not, we can always share like a GitHub link. So it's got all of those features, plus a few more that I list here. Okay, but there are lots of alternatives. I don't know why I listed this as an alternative. So BCF is actually another BART-based approach by Harm, Carvalho, and Murray. It's great. You've probably heard of the GRF approach, the Athenian Vagar. This is one that did really well in a competition built by IBM folks, but available on R. Superlearner, the Berkeley folks have been working on Superlearner stuff for a long time, and they do great work. Great, very computationally intensive, but does typically quite well. This is our work with the sensitivity analysis, and XLearner, only a couple of years old, but doing great things. So lots of alternatives. We're certainly not the only game in town. Okay. Good. I have a little bit of time to talk about humans, because when we're doing research, it's not just the algorithm we use or the method we use, there's us, right? So we play a role in this, and it turns out, and there's our audience. It turns out that humans really want to interpret the world causally. So I challenge you to think over the next couple of days about how many times a day you ask or answer a causal question. For me, it might be like, what subway will I get there faster if I take the F train or the D train? Will I feel more sleepy if I eat this kind of breakfast or that? a million questions you pose and often answer for yourself without much evidence at all every single day. We are creatures that love causality, right? And that's how we make sense of the world. We make meaning in life by making causal attribution. So it's a really strong tendency. We really want to do it. We're constantly posing and answering causal questions. So just a few that have occupied me over the past months. If I get more sleep, will I be more productive? Is wine really that bad for me? Will exercise help my concentration? How many publications is enough? How much salt is too much salt? I say no amount. Should I send my child to private or public school? That's an old one. Will teaching well help or hurt my career? Should I take the A train or the D? Right? Just from, small little things in my everyday life to bigger life decision kinds of things, right? So here's some evidence about people liking to interpret things causally. So I'm citing, this is a, vast simplification of broad literature. People are more likely to understand and retain information if it's described using more causal connections. People explain and predict behavior similar to how they understand and tell stories. This requires understanding the sequence of events and making inferences about the mechanism behind each event. If someone's rude to you at a party, how many of you sit and think about, well, did I do something? Were they having a bad day? What happened there, right? We want to figure out the thing. Humans are better than other species at understanding causal connections and are prone to sharing those with others. People unconsciously use counterfactual simulation to understand how a situation could have played out differently, right? We're causal beings. Maybe that's what separates us from the animals, is the causal reasoning. So oddly, this has implications for how we present our research findings. So there have actually been a bunch of experiments about causal language and how it's interpreted, often using headlines in newspapers or using that kind of framework, exposing people to different headlines and seeing how what they interpret or how they would follow up in actions based on those things. And generally they show that people choose causal explanations that match their pre-existing beliefs. Surprise, surprise. If you see a newspaper headline and it with a causal headline and you don't really know the science, but agrees with what you would like to believe, you're probably not as interested in tracking down that article in Science or American Journal of Public Health or wherever it is and making sure they did the methodology right. But if it says something that you really don't agree with, you might be more inclined to track down that article, right? We all want to confirm our priors. Okay, but we're fine, right? Because we train our students to communicate cautiously. We tell them to use words like association and not cause, right? That should be enough. Of course, then they also pair that word association very often with words like change, decrease, increase, gain, right? And we, our students, our colleagues in the social behavioral sciences, all over the place, use association throughout their papers and then have a policy recommendation at the end, right? Super common to see that happen. So are we really fooling anyone? Or are we really just trying to be stealth causal? Okay, so I feel like we need to base our recommendations about how you should communicate your research findings in Better Science. So our team is running a bunch of experiments to test out how these subtle differences that we as statisticians, when we're teaching, feel like make a big difference. Do they really make a big difference in how things are interpreted? So that's in development. We're struggling with our IRB right now, but anyway, hopefully we'll have some results on that sometime soon. All right, now we're at the shameless plug part. Good, I'm almost done. So related to this, the fact that it's hard to understand the causal reasoning, the fact that it's hard to know how to convey your results in an appropriate way that's transparent and honest and helpful. I'm with a team of people funded by the IES, we're building out software to help applied researchers make good choices regarding algorithms and their language. So think causal is going to look something like this as we're developing it. There's going to be a welcome screen, and that provides opportunities both to learn about different kinds of concepts, but also to perform analyses using all the BART tools that I just described to you. And say, right now you can do all that in BART Cause if you program in R, but if you're like the education researcher at the Department of Ed in Tulsa, and that wasn't part of your training, but you still want to be able to capitalize on these tools, well, look, you can just, have this nice point and click interface to help you load in your data, make sure all the data are kind of coded in the right way, decide what's the treatment and the response in the covariates, do some exploratory data analyses, to help you understand things like overlap, et cetera. And then provide you with help. Like if you don't understand what the overlap is, there's going to be a module that helps you understand that. You understand what a causal estimand is, you get to click on a button and it will jump you over to a module, a Shiny app, basically, that teaches you about causal estimands. So we are thinking that this kind of just-in-time learning is going to be more effective than expecting that people are going to read long manuals or read whatever paper gets published in a stats journal that researcher is never going to read, right? Okay, so the goal there is to provide scaffolded, user-friendly access to sophisticated causal inference tools, build in educational components for just-in-time learning, and to provide guidance on cautious interpretation of the results. So at the end, it'll say, here's your treatment effect estimate and your uncertainty. Here's some suggested language about how you could present this to your readers in a way that's honest, right? So that's the goal. We're only about less than a year in, but we've made a lot of progress. If anyone wants to know more or wants to collaborate on this, we'd love to hear from you. Or if you have, you teach causal inference or another stats class and you'd like to help us test out some of our learning modules, we would love that as well. So I'm just going to leave you with some calls to action. Encourage you to use new methods. That's kind of the duh part, right? But I encourage you also to be honest about your causal goals. Instead of this whole, we have to use the word association because we are worried we can't do something causal. Let's just be bold and say, no, my goal is something causal. I want to estimate something causal. I'm going to try to do that. Here are the caveats. Here are the limitations. Here, every time you put your interpretation, you also say, but that assumes all these other things, and reinforce what the assumptions are. I think that's the most honest and transparent way to help your audience understand and interpret your results. Okay, so thank you, and here's some additional references.
Thank you very much, Professor Hill.